In this lecture, we are going to discuss about the last type, that is the vestigial sideband, where we will discuss the transmitter of the vestigial sideband and the receiver of the vestigial sideband as together. So let's discuss the transmitter. For the transmitter, we use balanced modulator, so M of T, and for the balanced modulator, you are also multiplying with the cos omega Ct. Balanced modulator is multiplying the message signal and the carrier signal, and then we are basically representing the signals in terms of the frequency domain rather than the time domain. So that is why it is x of f, and the frequency domain of the message signal is m of f. So similarly, the output of the balanced modulator x of f is going to input in the sideband filter whose frequency is h of f, and then at the output you are getting y of f, which is the vestigial sideband signal. On the receiving side, we again use the synchronized detection. So synchronized detection means the balanced modulator followed by the low pass filter. So the y of f will be the input of the balanced modulator, and again the locally generated carrier, synchronized carrier signal cos omega Ct, and then the output of that is z of f, and then you will pass that z of f from the low pass filter, and then you will end up at the message signal, which is S of f, or you can say m of f. So let's start x of f. So x of f is basically, so if you want to write in term of frequency domain, you know that the message signal is shifted to this double sideband. So the double sideband means this shifted, your message signal is shifted to the frequency of the, like the lower sideband and the upper sideband. So it's shifted to the frequency. So it is in the frequency domain mf minus fc plus mf plus fc. Usually if you pass the signal in terms of the frequency domain, then the signal gets multiplied, but in time domain they get in convolved. So we are doing in a frequency domain, so that is why the signal gets multiplied. Y of f, so the output of the sideband filter is y of f, which is the multiplication of x of f multiplied by h of f. So x of f multiplied by h of f, and the output of the balanced modulator at the receiver. So the output of the balanced modulator at the receiver will be the multiplication of y of f and the cos of omega t. And if you want to write in terms of the frequency domain, so the z of f, again you are doing the same thing, y of f minus fc and f plus fc. It is again shifting like a double sideband signal, so it is again shifting. So if you so in this from here, so you can see that your y of f is basically x of f multiplied by h of f. So x of f is the x f minus fc multiplied by h f minus fc. You are just inserting this frequency in this equation, and then plus, so this format, so x f of fc and then multiplied by h I f plus fc. So x a, so this was equation a. So x of f can be calculated using a, where you substitute f is equals to f minus fc. So z of f, now here, so this is z of f. So z of f is basically equals to 1 over 4, because we are inserting the value of x of f from here. So x of f is in the format of m. So mf minus 2fc, because we are writing f is equals to f minus fc. So f, if you insert f is equals to f minus fc, so that will becomes like here. So if you insert, so this f is equals to f minus fc, so fc is already there, minus fc, that will be equals to f minus 2fc. So that is why this is f minus 2fc, because you are substituting f as f minus fc. So similarly here m f minus fc plus fc, so that will cancel out, and then multiplied h of f minus fc. Similarly on the other side, so f plus fc, and then so you see this is also cancel out, and you have m f plus 2fc and hi f plus fc. So we have m f minus 2fc plus m of f, and then this filter response plus, so and this part, and then the lower frequency and then the filter response. So when you pass that signal through the low pass filter, so the frequency of that is bigger than FM, and similarly the frequency of that is again bigger than FM, so it will not pass, so rather this will pass. So that is why 1/4, so M of F is common in both of them, so that is why I take common M of F, the remaining is H of F I, so this part, and that is this part, so this is S of F at the output of the filter. So this is the extra part. So you see, this is the required signal that was transmitted from the transmitter, but this one is extra. This one is extra part which can be removed using the, either you can use equalizer at the output of the low pass filter, or you can make the low pass filter such that this extra part could be cancelled at the low pass filter. Otherwise you should design equalizer or use equalizer whose characteristic is something like this, like H of E of F is equals to 1 divided by H of F minus Fc plus H of F plus Fc, and then if you multiply the equalizer output with that B equation, then they get cancelled out, and then the remaining is 1/4 M of F, so which is the required output at the receiver. So that's all. This part has been completed. The amplitude modulation has been completed, and I hope that you enjoy reading or watching our videos. So but if you still have any question throughout the amplitude modulations signals, so you can ask questions, so you're most welcome. You can write the comments in the comment box, and we will try our best to answer your questions. Thank you for watching the video.